I'm just going to test to make sure this is picking up. Perfect. Okay, so the second portion of our acids and bases unit covers neutralization reactions. In a neutralization reaction, an acid reacts with a base to form a salt and water, which is old news. We already talked about that in the first portion of our acids and bases unit. Neutralization reactions. Like I said, in a neutralization reaction, an acid reacts with a base to form a salt and water. You pass that back. Neutralization is defined as the point when the moles of acid or hydrogen ions equals the moles of base or hydroxide ions. We would normally think that a neutralization reaction would yield a solution that would have a pH of 7, because the hydrogen ions would react with the hydroxide ions, we'd form salt and water, and we'd have a neutral solution. But this is not always true. The salt that is formed from the neutralization reaction can actually affect the pH of the solution. We'll talk about how that happens and why that happens shortly. As we've already seen, an acid and a base will form salt and water. The cation that's in the salt formed from an acid reacting with a base is a conjugate acid. And it has the ability to react with water. Sometimes this conjugate acid produced is a strong conjugate acid, and sometimes it's a weak conjugate acid. If it's a strong conjugate acid, it's going to have a strong ability to react with water, and if it's a weak conjugate acid, it will not. The stronger the base is, the weaker the conjugate acid in the salt will be. The weaker the base is, the stronger the conjugate acid in the salt will be. The anion in the salt will be a conjugate base from the acid, and it too can react with water. The stronger the acid is, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. Now, depending on what sort of conjugates we have within the salt, they may be able to react with water, which will affect the pH, and they may not be able to. So we'll take a look at different types of reactions between acids and bases, and we'll look at how the solution's pH would be affected depending on the salt that's formed. Like I said, we're primarily going to focus on problem solving during the second portion of the acids and bases unit. And so let's take a look at a problem. We're going to start by looking at a strong acid and a strong base reacting in a neutralization reaction. If a strong acid reacts with a strong base, the salt that is produced will not affect the pH of the neutralized solution, and therefore the pH would be 7. The cation of the salt comes from a strong base and is therefore a weak conjugate acid. Because it's a weak conjugate acid, it doesn't have a significant ability to react with water. The anion comes from a strong acid and is therefore a weak conjugate base, and therefore does not have a significant ability to react with water. Because the salt does not react with water, the salt will not play a role in changing the pH of that neutral solution, so the pH will be 7. Let's consider a neutralization reaction between sodium hydroxide and nitric acid. Now, the heading on the slide says a strong acid is reacting with a strong base, but you're not going to have those kind of headings in your practice test or on your actual test. So the very first thing that you want to do when you look at a neutralization reaction between an acid and a base is decide what kind of acid is it and what kind of base is it. If I didn't have the heading of strong acid and strong base, how would I know that sodium hydroxide is a strong base? It has hydroxide ions. It's a hydroxide-containing compound. So strong bases are hydroxide-containing compounds. How would I have known that nitric acid is a strong acid? Because there's a list of 4 strong acids that you just have to know. Can somebody tell me those 4? Perchloric, I heard. Hydrochloric. No, sulfuric. And obviously, nitric. So we have a strong base, strong acid. Let's write the reaction. Sodium hydroxide, NaOH. Reacts with nitric acid, HNO3. Double replacement reaction. The hydrogen and the sodium are going to switch places. Sodium is now going to be paired with nitrate. This is our salt. And hydrogen will be paired with hydroxide, HOH, which is water. The cation in this salt is a conjugate acid. The sodium comes from sodium hydroxide. This is a strong base, which makes this a weak conjugate acid. The anion in the salt is a conjugate base. It comes from the nitric acid. This being a strong acid makes this conjugate base a weak conjugate base. Because this conjugate acid and this conjugate base are both weak, they will not have a significant ability to interact with water, so they will not have the ability to change the pH of our neutralized solution. So neither the conjugate acid or the conjugate base will change the pH of the neutralized solution. This is going to allow us then to ignore the salt when we're making calculations relative to this particular reaction and the pH of the solution at various points of the reaction. That won't always be the case. Let's look at the complete neutralization of sodium hydroxide and nitric acid. This is often referred to as the equivalence point. The reason why it's referred to as the equivalence point is because it's when the moles of acid, of hydrogen ions, are equivalent or equal to the moles of base or hydroxide ions. When you're taking your notes, it will be really beneficial for you to make really nice, big, bold headings, very clear distinctions between different types of problems. So if I were taking these notes, I would want in my notebook to have a very strong indication that I am solving a strong acid plus a strong base problem, and that I'm doing a complete neutralization of a strong acid and a strong base for this particular problem. This will help you then when you're looking at your practice test or when you're studying for your test and you have a problem in front of you where you see a strong acid and a strong base and a complete neutralization. It will help you find a reference place then in your notes to help you solve that problem. 2 other tips. 1, solve with me. Take out your calculators and do all of the calculations with me. And ask questions if you don't understand. Where did you get that number from? How did you get that? Why did you do that like that? And tip number 2, if you think you're not going to remember where a number came from, when you look at your notes later, take time and write what that number referred to or why you did a step the way that you did it in your notebook. These practice problems we do in class are going to be very, very helpful when you do your practice tests and when you're studying for your test. But if you take a look at it in a week when you're starting to do your practice test and you go, God, I have no idea why I did that or what I even did, it's not going to be helpful at all. The question says, how many moles of 0.100 molar sodium, and it should be hydroxide, excuse me, is required to completely neutralize 50 milliliters of 0.200 molar nitric acid, and what would the pH of the solution be? true about the point of neutralization that might help me start solving this problem. I need to figure out how much of the base, sodium hydroxide, I need to neutralize the acid. I know the volume and the molarity of the acid. I only know the molarity of the sodium hydroxide. I'm looking for the volume of it that I would need to neutralize it. Well, we know the second question right off the bat. The pH of the solution will be 7. We have a strong acid and a strong base, and we have a completely neutralized solution, so the pH has to be 7. So that answers the second question, but what about the first? What do we know about the point of neutralization that might help us solve this? Moles of acid is equal to moles of base. So we can use the fact that we have 50 milliliters of 0.2 molar nitric acid to find out how many moles of acid we have present in the solution. That has to equal the moles of base. If we know the moles of base and the molarity of the base, we can find the volume of base needed to do this neutralization. So we need to find moles of acid. If I know volume and molarity, how do I find moles? What's the equation? Molarity is equal to moles per volume in liters. So how do I find moles? Molarity times volume. So if I want to find how many moles of acid I have, I'm going to need to multiply the molarity times the volume. The volume's got to be in liters. So 0.200 molar times 0.0500 liters will give me moles of nitric acid. Point 0.01. Because this is a monoprotic acid, I know that I also have 0.01 moles of hydrogen ions. And I know this is a 1-to-1 ratio. This is a base that dissociates in a 1-to-1 ratio. So for every one hydrogen ion, I need one hydroxide ion. So the moles of sodium hydroxide should be equal to then the moles of acid. Rather than having to reason that in your head, though, you can rely on using the mole-to-mole ratio in the balanced equation to figure this out. You can just simply look at, if I need 0.0100 moles of acid to be neutralized, because this is a 1-to-1 ratio in the balanced equation, for every 1 mole of hydrogen ions, I need 1 mole of hydroxide ions. You can say that for every 1 mole of HNO3, there is 1 mole of NaOH. So 0.0100 moles of NaOH is needed to neutralize 0.0100 moles of HNO3. Again, because it's a 1-to-1 ratio here. Now I have moles of sodium hydroxide, and I know the molarity of sodium hydroxide. If I know moles and I know molarity, how do I find volume? Moles over molarity. So 0.0100 moles of sodium hydroxide divided by the molarity of this sodium hydroxide. Our sodium hydroxide is 0.100 molar, so divided by 0.100 molar will give us the volume in liters of sodium hydroxide required to neutralize that acid solution. So what's 0.01 divided by 0.1? 0.100 liters of sodium hydroxide, which is 100 milliliters of sodium hydroxide. Looking at significant figures, I've got 3 here, I've got 3 here, and 3 here. So I need 3 in my final answer. With 0.100 or 100 point, I have 3 sig figs. So it would take 100 milliliters of this sodium hydroxide to neutralize the 50 milliliters of nitric acid. And the pH would be 7. Questions? Okay, I'm going to give you guys a minute or two. Take any additional notes you need to take about where we got numbers from, why we did what we did, anything that would help you when you return to those notes later. Salsa. Yes, I'm usually specific, especially on a test. I'll be specific about what I would like it to be in. The reason why I converted to milliliters is because on the next couple slides, we're going to be working with milliliters, and we're going to be comparing to this neutralization point. And so I want it just to make it easier on us. When you are finished adding in any notes you want to add in, let's look at a problem where we are partially neutralizing a solution. What do you think partially neutralizing a solution implies? It's not completely neutralized. So we're on the way to neutralizing the solution completely, but we have not reached the point of neutralization. How many milliliters did we say we needed to completely neutralize the solution? And this is the same set of numbers we were working with on the previous slide. How many milliliters do we need to completely neutralize? 100. So if we only add 20 milliliters, so we have not yet added 100 milliliters. If we've only added 20 milliliters, we will not have completely neutralized the solution, which is why this is a partial neutralization. We'll be 80 milliliters shy of neutralization if we've only added 20 and we need to add 100. In a partial neutralization, in this particular problem, the base that we add is going to neutralize some of the acid, but will all of the acid be neutralized? No. There's going to be acid remaining after the 20 milliliters of sodium hydroxide have been added. That acid that's remaining after the 20 milliliters of sodium hydroxide are added is going to affect the pH of the solution. If there's acid present still after we've added in the sodium hydroxide, what kind of pH value are we going to see, just very generally? For a complete neutralization with a strong acid and a strong base, a pH of 7. For this particular problem, if we have acid remaining after we've added the base, what kind of pH should we see? Should be less than 7, which would indicate an acidic solution because there's still acid present. So we should see a pH that's less than 7. Well, we can figure out how many moles of sodium hydroxide we're adding and how many moles of nitric acid we have using the volume and molarity of each. This will allow us then to figure out how much acid we have left over. We know that for every 1 mole of sodium hydroxide, there's 1 mole of nitric acid. So we can see how many moles of sodium hydroxide we've added, how many moles of nitric acid we have, and we can see how many moles then would be left over. So let's do that. Let's start with moles of sodium hydroxide. Again, moles will be volume times molarity. So 0.100 molar times 0.0200 liters. 0.00200 moles of NaOH. And we can see how many moles of acid we have. Oops, should be 0.01. So the 0.002 moles of sodium hydroxide that we have will go into neutralizing some of this 0.01 moles. How much will not be neutralized? If this is a 1-to-1 ratio. .08. If this neutralizes in a 1-to-1 ratio, this 0.002 will neutralize 0.002 moles of acid. If 0.002 moles of acid are neutralized, there'll be 0.008 moles remaining. So minus 0.00200 moles that will be neutralized will leave us with 0.00800 moles of acid that is not neutralized. And this non-neutralized acid is going to be what affects the pH of the solution. If we need to calculate pH, how do we do that? Negative log of the hydrogen ion or hydronium ion concentration. And what is true about the hydronium ion concentration if we have a strong acid like we have in this particular problem? Equal to the concentration of the acid. So we need to know what concentration of acid do we have that is not neutralized. So we have to figure out, let's see here, what concentration of acid is not neutralized. Well, we know that we have 0.00800 moles of nitric acid not neutralized. So we know how many moles we have. What's the other piece that we need to find concentration? The volume. What is the total volume that this 0.00800 moles is in after we've added the acid to the base? 70 milliliters. So to calculate the molarity of the nitric acid, we're going to take 0.00800 moles of HNO3 divided by 0.0700 liters. So the concentration of the HNO3 that is not neutralized will be 0.00800 divided by 0.0700 liters. When I calculated that, I got 0.114285714 molar. Now we know, Morgan. You could write not neutralized, and that's fine, but you wouldn't have to specifically note that. We know then that because this is the acid concentration, it's also the hydronium ion concentration. And so we can find the pH by plugging that in. Now looking at significant figures, if we look at the problem, it looks like we should have we have three sig figs in each of our values, which means we should have how many decimal places in our pH? 3. With 3 decimal places, what is our pH calculated to be? 0.942. Very acidic. But that should make sense because we're 80 milliliters shy of reaching neutralization. If you need to, take a couple minutes and add in some notes. Where did this 0.07 come from? Why did we need to find this? Why did we do this like this? Whatever you need to add in so that when you come back to this for studying later, you understand why we did the work we did. When you finish adding in the notes that you have, or go ahead, Emily. The reason why we know the pH has to be less than 7 is because we know that if we don't add enough base to neutralize all the acid, there's going to be acid remaining. And according to the pH scale, an acidic solution has a pH less than 7. If there's acid remaining, the solution is going to be acidic, so the pH is less than 7. This helps us kind of identify where we should be when we calculate. So if we got something that was above 7, we'd know we calculated something wrong. We're going to do another partial neutralization. We're going to look at the halfway point. What do you think the halfway point is? No, not necessarily. Halfway point. Complete neutralization, we have a pH of 7. The pH will not necessarily be 3.5. Remember that pH is a logarithmic scale, so it's a base of 10, which is why it wouldn't be a pH of 3.5, which is that's a common misconception. What does the halfway point imply? Halfway to neutralization. Halfway to neutralization. If we are halfway to neutralization, how many milliliters did it take us to add or to completely neutralize? Our first problem that we did, complete neutralization, how many milliliters did it require? 100. So what's the halfway point? 50. So we're adding half of the volume that we need for neutralization. That's the only thing implied by halfway. And I asked that the way I asked that on purpose to get through all that stuff that students sometimes think the halfway point implies. The halfway point simply implies half of the volume required for neutralization. So in this particular problem, 50 milliliters, because as we calculated in the first problem, 100 milliliters is needed for complete neutralization. This problem is going to be just like the last. So don't let the halfway point complicate things for you. Just like with the last problem, we have partial neutralization. So you'll have to calculate how many moles of acid you have, how many moles of base you have, how many moles of acid won't be neutralized, and then find the concentration, and then find pH. I'm going to let you guys try this one on your own and see if you can come up with the correct answer. This is where we will start tomorrow. I will briefly go over this problem. So make sure that you work it out in your notes now so that you have this as a reference later, and then you can keep up tomorrow when I go over this rather quickly.